Okay, this is our third video on the wave properties of light, and we would like to investigate what happens to waves when they strike a material. So let's go ahead and talk about a new topic that is super important, and it is called the index of refraction. So the index of refraction is defined as the change, essentially the ratio of the change in the speed of light as it strikes an object. We mentioned to you in a previous video that the speed of light does change, at least macroscopically. The resultant speed of light changes when it goes inside something like, let's say, glass. And so, I mean, obviously, if it goes into something completely opaque, the speed of light it's basically the photons are absorbed and you don't get anything. But if it transmits through the material, then we can see it's still moving, it still has motion, but that the amount of time that it takes a particular photon to get from one side of the material to the other is longer than it would have been in a vacuum. All materials have an index of refraction associated with them. Let's go ahead and give our definition. It is given as a lowercase n, and it's defined as the speed of light in a vacuum, c, divided by the speed of light in a material. So, in other words, if you have that piece of glass that I just mentioned, the velocity of light in that speed of glass will be corresponding to the index of refraction of glass. Okay, so all materials, we can label as having these different indices of refraction. Those are not something that we determine by first principles. They're something that we determine by experimental evidence. So here's a table. Vacuum has an index of refraction of 1 by definition, because then the speed of light in a vacuum is c, so you'd have c over c, which makes the index of refraction equal to 1 for vacuum. If we wanted to know how fast then a photon moves in ice, then we would say we know that the index of refraction for ice is equal to 1.31, and so the speed of light the speed of light in ice is equal to just rearrange this equation, right? So we would need to solve for v, in other words, and we'd have c, the speed of light in a vacuum, divided by our index of refraction. So we would have 3 times 10 to the 8 meters per second divided by our index of refraction, which is 1.31. That is because I rearranged this. And so that would give us the slightly reduced speed of 0.29 times 10 to the 8 meters per second in ice. Not particularly noticeable to the human eye, but we will actually be looking at index of refraction in different terms next week. It's a really important feature of materials, and I think that it'll be much more useful for calculations next week when we start to look at what happens to a group of photons when they hit materials at different angles. But for this week, we're interested in studying what happens due to index of refraction of a material in terms of frequency and wavelength. Let's address frequency first. If you don't understand the frequency, then it's harder for you to figure out the rest of the stuff. Frequency is really simple if you can remember it. If you can't, then I need you to think through it in this way. I have a piece of material here. You could call it glass or glass or whatever you like. Like glass there. When we have a photon coming into our material, then you may remember that the frequency was determined by how rapidly the peaks hit the material. So, tick, 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 tick. If you have 100 wavelengths going into the material in a certain amount of time, those wavelengths have to be going out of the material in that certain amount of time. And so that means that the frequency inside the material has to be the same as the frequency outside the material. So what I'm going to do is I'm going to label this outside the material, outside the material, outside the material, and we're going to look at what those are inside the material in comparison. Now, the velocity outside the material is, of course, just c. We know that the velocity outside the material then is going to be equal to, according to this equation here, the velocity inside the material times the index of refraction n. Our frequency we just looked at logically and found that that is equal to the frequency inside the material. So our remaining question is, what is the wavelength inside the material? Well, the wavelength inside the material is a little bit odd. We can mathematically prove this one. So we know that another equation that we ran into on the last video was the velocity, and that could be outside or inside or whatever, but velocity of waves is always going to be equal to lambda, the wavelength, times the frequency. So what I'm doing here is I'm writing subscripts m so that you can notice that the velocity inside the material is equal to the wavelength inside the material times the frequency inside the material. But always make sure your subscripts line up here. We could also say, according to these, that the c is equal to the wavelength outside the material times the frequency outside the material. So let's go ahead and look at this in terms of our wavelength inside the material. How do we find that? Our wavelength inside the material is equal to the velocity inside the material divided by the frequency inside the material, which I'm just going to write as f because, well, it doesn't seem to matter whether it's inside or outside the material. Well, now what's the velocity inside the material? That's easily found right here. The velocity inside the material, or here. The velocity inside the material is the speed of light over the index of refraction, right? So c over n times the frequency, right? Then we can also look at the fact that outside the material, c is equal to lambda outside the material times the frequency, right? And so if we were to divide that equation by the frequency, look what we find here. We can replace c over the frequency with simply that. Now that's interesting because what it tells us then is that the wavelength outside the material is equal to the index of refraction times the wavelength inside the material. Now you're going to see this a little bit differently on your equation sheet. What you may notice here is if you take the index of refraction of material times the wavelength in that material, that is always going to be equal to the index of refraction of a different material times the wavelength in that material times the index of refraction of a fourth material times the wavelength in that fourth material, and so on, right? So that's a useful equation. And on your equation sheet it's written like this, but you can always remember that if the index of refraction of the first material is 1, then that means that its wavelength is equal to the wavelength in vacuum. Okay, so what does it look like? Well, you kind of notice here that inside the material our wavelength is actually diminished by some amount. N is always greater than 1, so if n is always greater than 1, then that means that we have a shorter wavelength inside the material than we do outside the material. Now, does that mean that it's a higher energy? It does not. It doesn't mean it's a higher energy because remember that the speed has decreased, the frequency has stayed the same. So if we were to look at this in terms of energy, which of course we can, we'd say, okay, what is the energy in here? That is equal to Planck's constant times the frequency. We could also look at that as Planck's constant times c over lambda. That's going to be the energy outside the material. If we were to look at it inside the material, Planck's constant has not changed, right? The frequency has not changed, right? If we were to look at it inside the material using the second portion of the equation, well, then we would say Planck's constant has not changed. Has c changed? Why, yes, it has. It's changed to some velocity inside the material. Has the wavelength changed? Why, yes, it has, by the wavelength in the material. And so those would have scaled together by a factor n. So the energy stays the same. Although I have mentioned that the speed of light changes in a material, there is the theory of Huygens' principle. I hope I'm spelling this guy's name right. He's sure to put a lot of work into this. I know I'm not saying it right. Huygens' principle is essentially what I call like a pinball principle. So essentially, the photon itself does not change its speed if you were to be able to measure the speed of the photon at any point in the material. But what it does is, if we took array of light, the rays of light are going to bounce well, not really bounce, it's much more organized than that, but it forms these sort of wave fronts, okay, and those wave fronts then stack up. So while the wave fronts are moving at the speed of light, the way that they stack up and preserve the information is actually moving slower than the waves themselves. So it's really kind of a net result that we see in the material, and not actually slowing down. Now, in this course, we're not going to go into the specifics of Huygens principle. I want you to know that it exists and it's interesting, but what we're going to do is simply say in a macroscopic way, hey, guess what? The velocity of that thing slows down. Why? Because what we're interested in is if you send light through the first side of your material, you want to count how long it takes to get to the next side of the material. That's essentially what we're after. So this is the principle behind index of refraction. It is loosely connected to the density of objects, although there's other factors involved. So you can sort of presume that denser objects are going to have a greater index of refraction. You can see here diamond has an index of refraction of 2.4, but there are actually denser objects that have a lesser index of refraction because of the way that this is because of the way that diamond is constructed electrostatically. So, okay, if you have any questions on this week's material, which is the behavior of the waves of light and the concept of photons, please reach out to me. I'd be glad to answer the class as a whole or students individually.